My name is Doug Creager. I work at GitHub. I manage the semantic code team. Our team's remit is to find interesting bits of academic research, in particular program analysis research, and to try to find ways to incorporate those into interesting product features at GitHub. And so today I'm going to talk about some work that we've been doing over the past couple of years to bring a more precise version of code navigation to github.com. And the work that I'm going to describe today builds very much on this framework called scope graphs, which was developed by Elko Visser's research group at TU Delft. So if you want to learn more about the academic work that this is all based on, I encourage you to check out the project website. And also, Professor Visser did speak about scope graphs 4 years ago at Curion, Barcelona. So if you want to learn more, you can also go look at his talk there. It's recorded on YouTube. And I definitely encourage you to check it out. I mentioned that we're sort of working towards code navigation. So just very briefly, I want to make sure that we're all on the same page about what that means, what that involves as far as a product feature. So here we have an example Python program. I'm going to be showing a lot of example programs throughout this talk. Most of them will be in Python, but the expectation is not that you're a Python expert. I'm not trying to do anything deep with the semantics of Python in particular. I just had to choose a language for the examples, and this is a good one. And so here we have a very simple file. There's 3 functions defined in it. We have a reference at the end of the file. This is building on the fact that a lot of the things that our programs build upon are names. We have entities that we're creating in our programs, and we have to give them names so that in other parts of our program we can refer back to those things. Here it happens to be functions, but we also have local variables, classes, modules, all sorts of things that we might need to talk about in our programs. And we typically use names to do so. So what I've done here is I've highlighted in red a definition. That's where we're using a name to create this new entity, in this case a function. Later in the file, as I said, there's this blue highlighted name. It's still Broil. This is a reference. And what we're trying to do here is detect and encode the fact that that reference refers back to the definition in question. So if you were to execute this Python file, when you get to that last line, we see this name Broil. The Python interpreter is going to go look for the thing named Broil, see that it's a function, see that it's that particular function, and then go through and execute its function body. So code navigation consists of a number of different interesting features. The ones you're probably most familiar with are jump to definition and find all references. Jump to definition is a feature where you could click on that blue name in your editor locally or on a website like GitHub. And what it'll do is it will take you to the definition that we think that that name refers to. The inverse of that, find all references, would allow you to click on the red name, the definition, and find all of the occurrences in your program where there are names that refer back to that function. Now that's like pretty basic stuff. There's other things that you can do with this information, because really what you're producing is a record of the entire call graph of your program. All of the different functions, all of the different classes, the way that the different pieces of your code interact with each other and with your dependencies. And you can think of a lot of other interesting features that could build upon that data set if you have it available. But just for today, we're going to talk about those 2 basic code navigation features just as a way of grounding our discussion in something relatively simple. So why is this hard? I showed a pretty simple example here where it was pretty obvious what the reference refers back to. So I want to start walking through some more complex examples where it's not, well, it'll be clear to us as humans, but it's not necessarily clear how to detect that programmatically. So now the first more complex example. If you have eagle eyes, you might spot the difference here. This is very similar to the first example. The only thing that we've changed is that that first definition is now broil instead of bake. And what that means is that we now have 2 definitions in this file with the same name. There's 2 functions that are called broil. And what are we going to do in this case? This actually depends specifically on the fact that we're using Python for this example. In Python, the rules are that the later definition overwrites or shadows the earlier definition. And so if you were to click on the reference at the end, you would want it to show the second of the 2, not the first. If we switch languages, though, and we look at this example in Rust instead, it's exactly the same thing, just sort of transcribed into a different language. Interestingly, in Rust, this is a compile error. If you tried to take this program and compile it, Rust will tell you that you're not allowed to have multiple definitions at the same scope with the same name, and it will flag this as an error. So this is, again, highlighting the fact that the rules that we have for constructing this data are going to depend on the particular language that we're looking at. It's not something where we can create a single universal set of rules that apply across all of the languages that we're looking at. We can also make this more complex by breaking the content up into multiple files, because it's very, very unlikely that you're working on any real code base that's isolated to a single file, right? So here what we've done is we have the reference in the file on the right, and we have the definition in the file on the left. And we should be able to sort of trace through this import statement to see that the reference refers to the definition over in stove.py. And again, this is building upon some language-specific intuition that we have about how import statements are structured and what particular names they bring into scope from other files. We can take this a step further and separate this into multiple packages or repositories. So here I've tried to use these emojis here to represent package names. So we have down in the lower right corner chef.py, that's where the reference is. It's in this package which has the sort of chef emoji as its identifier. The definition is up in the package in the upper left. We've introduced a third file here as well, along with what I like to call a re-export statement. So if you're not familiar with Python, what that middle kitchen.py file is doing is it's loading in all of the symbols from stove.py and making them available under the kitchen module as well. And so what that means is that we can trace this path from the reference all the way up to the definition. We have to go through a couple of import statements. We have to go through a number of files, but eventually we do land at the definition like we were before. Another way that this example is interesting, though, is that you might come along and change the content of kitchen.py. And this is sort of highlighting how we're building code navigation specifically for a hosted website like GitHub and not necessarily for a local editor. What is interesting here is that now we have two definitions of broil. So you might imagine that what happened is that the package owners have discovered that there's something weird going on with the broil function. And so they've introduced some logging just so that they can see when it's being invoked. And you might imagine more complex logging. I just used a print statement here to keep the example simple. But what this does is it changes the name binding. The reference down in chef.py now lands on this new function that was introduced in kitchen.py. And this is important because it was not the file that contains the reference that changed, and it was not the file that contained the original definition that changed. It was this intermediate file that we had to move through along the way from the reference to the definition that changed. And so that means that in the naive case, anytime any file in your repository or in any of your transitive dependencies changes, we might have to go through and recalculate these results to see what our references are landing on. Okay, one last complex example. Here we're adding classes, Python classes. And the reason for that is that we want to show that we still want to click on broil, we still want it to resolve up here into the stove.py on the left, but now it's not a function at the top file level scope. It's actually an instance method inside of a class defined inside that file. So now over at the reference, you can see that we're not just calling broil directly, we're calling broil on this stove local variable. And what that means is the path is much more complex. Right? As we start to figure out what broil refers to, we have to pause the lookup of broil and start doing a lookup of stove, this local variable. Because what it is, what its content is going to affect what broil might resolve to. Because you might have a different thing that has members that you need to go find what it is and then be able to see what broil member is in there. So we have to pause our lookup of broil, start looking up lowercase stove. In this case, we're lucky because it's just defined as a local variable one line up, but that might not be the case. It might be defined anywhere. Having seen that it's this local variable, we now have to see what its value is. In this case, the value is the result of calling this capital S stove. So now we have to pause our lookup again and go figure out what that is. Like we were doing before, we can move through these multiple import statements to go find the definition of capital S stove in stove.py. And we can see that it's a class. So now again, we have to bring in our knowledge of Python to know that when you invoke a class, what you get is an instance, a new instance of that class. It's like the new operator in Python. So now we can come back and see that that's what the result of this call step is, so that then we can go find the class definition and see that there's an instance member inside of it called broil. So we had to bounce back and forth between multiple files multiple times. We had to pause our lookup a couple of times in order to get subsidiary results, which our original lookup depended on, But we were eventually able to sort of land on the definition that we looked for, that we wanted to find. Okay, so is that all, right? So I've sort of shown some interesting examples where just the act of finding the necessary results that we care about can be complex. Is that all that we have to care about? And as you might expect, it's not. We also have this sort of non-functional requirement that we want this entire thing to be zero config. We are wanting to turn on precise code navigation as a feature for an entire ecosystem. We want to be able to say that we now know how to extract this information for Python, so we're just going to turn it on for all public and private Python repositories. It's not something where we want individual package owners to have to tell us how to collect the necessary data or to configure a CI job to produce that data for us. We want to be able to do that all by ourselves, sort of internally as an internal service, and have this just be a feature that just works. We also have to deal with scale. GitHub is a large website, right? There's a lot of code hosted there. Our most recent public numbers, we have 200 million repositories and counting. That's public and private. We have 2 billion contributions over the past year. Not all of those are pushes, are commits, but a lot of them are, like a substantial fraction of those are, and so that just shows the volume, the fire hose of incoming changes that we have to keep up with. And also interestingly, for this particular use case, we have a lot of programming languages that we need to worry about, right? A lot of the examples that I showed you, I talked about how we needed language-specific rules to know what data to extract. And if you look at Linguist, which is our open source repository that has language-specific information in it, it currently tracks around 500 programming languages. And a lot of those are only in support of things like language detection. You can't do anything more advanced with them. But it's just showing that there's this really long tail of programming languages, and we want to, in some way, be able to support all of them. So how are we going to do this? For a hosted service, what this means is we kind of have 2 phases of execution where we get to think about generating this data in support of user queries. We have index time, which is when the code is coming in, when it's pushed, right? When somebody pushes up a new change. And then we have query time, which is when a user is trying to navigate that code on the website. And it might be different people who are doing those 2 operations, right? The package owner or one of the contributors will be doing the event that triggers the index time behavior. But it's anyone at all who might be coming along and viewing this code and trying to explore it and figure out how it works. And so we have to figure out how to take this work that we have to do and divide it up amongst index time and query time in the most efficient way. And we have some constraints. We can't do too much work at query time because this is an interactive feature that we're trying to produce. We want it to actually be fast enough to generate the results as users are clicking around on the code view on github.com. And what that means is that we have a goal of around 100 milliseconds for the maximum amount of time that our query step can take. Anything more than that, and it starts to affect the human perceived latency, and it becomes too slow for an interactive feature. On the converse, we can't do too much work at index time because of all of those scale concerns that I just told you about. We have so much data being stored and coming in on an ongoing basis that we have to make sure that we are reusing work as much as we can. We can't be in a situation where we really do have to reindex every single thing in your repository and all of your transitive dependencies every time there's any minuscule change in any of them. That's just a non-starter, both in terms of the storage costs that would be needed and the compute costs to calculate that data. What we want to do is we want to find a way to strike a balance. We have to do as much pre-calculation as we can at index time, and we want to minimize the amount of duplicated work so that we can reuse results as much as possible. And in order to do that, if we need to defer some amount of work to query time, that's okay, as long as we don't defer so much work that we end up exceeding that 100 millisecond budget for queries. And incremental processing is sort of how we do that. We're leaning into the fact that we're calculating this data for Git content. Git's data model provides a very nice, friendly way of doing this kind of idempotent work, if you will. When a typical commit comes in, it's very likely that that commit has only changed a small number of the files in your repository. And all of the other files in your repo have the same content and live at the same locations that they did before. And so our goal is to reuse results that we've already calculated for any of those unchanged files. And in particular, it's not just the storage that we're trying to save. So you could imagine that you're going to go through and actually spend the compute to analyze everything, and you'll see that the results that you got for a particular file aren't different than what you had before. So okay, we don't need to store a new copy of that data. It's already there. But we're trying to take it a step further and actually save on the compute as well. We want to be able to see from the Git data itself that a file hasn't changed and know that the results that we had already calculated for that file are still valid and can be reused without having to do any work for those files at all at index time. Okay, so to summarize, we've spent a fair bit of time now talking about why this is a hard problem. We've talked about how there are language-specific rules that can be quite complex that we have to take into account while we generate this data. We've talked about how the results can depend on intermediate files, and so that can be viral if you're not careful in terms of when and how you have to recalculate things. We've talked about how we want this to be a zero config, it just works kind of feature. And then we've talked about how in particular we need incremental processing in order to do all of this at scale. So how are we going to do this in a way that satisfies all 5 of these checkboxes? So I want to start to, in a sort of conceptual way, just sort of in English, let's look at this problem a little bit deeper. What would incremental results for code navigation look like? So let's go back to one of our simple examples. This is the one where the reference and the definition are in separate files, but we're not doing anything else more complex. What we want to do, again, incremental, that means that we have to look at individual files completely in isolation, and we can't look at any of the other files in our repository or in any of our dependencies. So looking at individual files, what information can we use to describe the content of the source code? So looking first at stove.py, we can look at this in isolation and say that there is a symbol called stove.broil defined at this particular location. We don't need any information from other files to see that. Similarly, if we look at kitchen.py, we can see that there is a reference on line 3, and because of the import statement, we can see that that reference refers to some symbol called stove.broil. And because it's in an import statement, we know that the definition of that symbol is in some other file. We don't know what file that is because we can't look at any of the other files in our repository or dependencies, but we know that it needs to exist and there needs to be this symbol defined somewhere in it for this reference to land correctly somewhere. And what's nice is that we can actually combine those two facts, right? You can sort of use stove.broil, if you will, as a join key or something like that that allows you to merge together or link together those two statements. And what you get if you combine the two is the sort of like derived fact at the end, which is that the reference at kitchenpy 3.1 is defined at stovepy 4.5. And so this is showing how we've done some of the work at index time. That's where we generated those facts looking only at individual files. And then at query time, we loaded in those facts and merged them together to get our final code navigation lookup results. Okay, so we can do this with the more complex example as well. We're going to do the exact same process. We're going to look at files individually and see what English language facts we can use to describe them. So first, for stove.py, there's actually going to be two facts here that we care about. The first is that you can invoke stove.stove, and we know that the name, the fully qualified name stove.stove comes both from the name of the class in the class definition and also from the name of the file, because in Python, it's the file name that determines the name of the module in that file. If you invoke stove.stove, what you get is an instance of the stove class. And we know that part of the fact because of our knowledge of Python, that classes are things that you can invoke. When you do so, you get an instance of the class. The other fact that we have in this file is that the stove class has an instance member named broil, which is defined at a particular location. And again, this is just looking at the definition of the class. This is what it means to define instance members in Python, and so we can just sort of like encode that narratively in an English fact. Kitchen.py, this is the one with the re-import statement that we talked about. The fact that we're going to write about this one is that if you are looking for kitchen.anything at all, you might instead find it at stove.that same thing. And this is because the import star in Python does this re-export semantics that we talked about earlier. And then lastly, this is the most complex one in chef.py. We can see, and this is sort of encoding some of the stuff that we walked through manually as we traced the path a couple of slides back. If you can find what kitchen.stove resolves to, and those two names are coming from the content of the import statement, and then you can call that. Once you find out what stove is, we're going to try to call it. The result should have an instance member, sorry, I don't know that it's an instance member yet because I don't know that stove is a class because I'm not looking at any other files. But I know that it has some kind of member named broil because otherwise that dot syntax wouldn't work. And that member is what this broil reference at chef.py 47 resolves to. So this is a more complex fact. It has multiple clauses. It's talking about that fact that we have to pause our lookups and look up other things and get the results and do some stuff with it. But we can still write this out in English and understand what we're trying to do. And then similarly, we can do this combination step at query time to turn this into a real code navigation lookup result. So we have the long one, if you can find what kitchen.stove, et cetera. And then we have the rename fact that we talked about, where if you're looking for kitchen.anything, you can rename it and start looking for stove.anything. So we're going to go change that kitchen.stove in the first fact to stove.stove. So we're updating our fact as we go along with more information that we're pulling in about the files that we're looking at. The next fact that we're going to care about is that if you invoke stove.stove, what you get back is an instance of the stove class. So again, we can combine those together, substitute in, and so now what we have is the stove class needs to have that member named broil, and if you can find it, that's what the reference resolves to. And then our last fact is the one that says, well, it does. The stove class does have an instance member, and in particular, that instance member is this definition. And so combining those two together, you get the final fact, which is that the definition at stove.py 59 is what the reference resolves to. So it was multiple steps to sort of combine information. It's not always just going to be two things that combine together, but there still is this process where we can generate these facts incrementally, looking at individual files, and then at query time, we can load in the ones that we care about, do this merge step, and eventually, hopefully, land at a result. Okay, so let's start moving into not just talking about this conceptually with English facts. How are we going to actually do this programmatically with an actual process that a computer could execute? And now we're going to start talking about stack graphs. Okay, so we're looking at our simple example again. We're going to look at stove.py first. And what we're going to do here is we're going to create a graph structure. And the goal of this graph is to represent all of the interesting name binding information that we can express about this file. And you can see that there are nodes in the graph that correspond with the definitions in the file. So I'm using this red double-bordered rectangle. That's what we call a definition node. That's what each of the definitions in the file will have somewhere in the graph that we create for that file. It might be hard to see, but I've just highlighted the sort of linked list of 5 circular nodes in the middle there. That particular structure of nodes and how they're linked together is what encodes the fact that in Python, later definitions in a file shadow earlier ones. If we were creating this stack graph for a language like Rust, we would actually choose a different structure of nodes and edges in order to encode the fact that in Rust, all of the definitions are sort of part of a single file level scope, and there isn't any shadowing there, and instead you have conflicting definitions if you have the same names. And then lastly, again, as we mentioned in Python, the name of the module is determined by the name of the file containing the content. And so we have these nodes here saying that all of these definitions, their fully qualified name would include this stove module name. Now we're going to do the same thing for kitchen.py. We're going to create a graph for it as well. The references in a file also appear as nodes in the graph. In this case, I'm using blue and single borders to indicate references. The import statement translates into this gadget of nodes, and this particular shape is something that we will always create for this kind of import statement. And we'll see in the next slide how in particular this actually implements the semantics of a Python import statement. What we can do with those two graphs is we can merge them together, right? So I showed the graphs that we created in isolation. We can load them in and create sort of like a large graph, which is just the union of all of the nodes and edges from the two per file graphs that we created. And the only interesting wrinkle here is that that filled in black node, which is what we call the root node, is shared across all of the files. So as we pull in all of the files, their root nodes will get merged together into a single node. But in all other ways, the graph structure is sort of forming these cliques, where there is a portion of the graph which came from stove.py, and it is completely isolated from the portion of the graph that came from kitchen.py. But in all other ways, it's just a very simple take the two subgraphs for the two files and merge them together into a single graph. And having done so, the name binding that we had found earlier is a path in this graph. So the fact that we can go from the broil reference through these other nodes over to the broil definition is what represents the fact that that is a valid name binding lookup in this particular set of files. Now, it's not any path that works here, because if you notice, like, I could just create a path from broil to the saute definition, and that's not one of the lookup results that you might expect. So how are we going to rule that out? We're going to use this concept that we call a symbol stack. So as we walk through the edges in the path, we're going to maintain this symbol stack, which is representing the thing that we're currently looking for in order to finish this name binding lookup. So we start at the broil reference, and the thing that we're looking for is that symbol, broil. So in general, blue nodes are going to push things on to this symbol stack. And now we can start to move through the edges in the graph. When we get to a red node, we're going to try to pop something off the top of the symbol stack. And what that means is that the symbol at the top of the stack has to match the content of the node. Otherwise, this isn't going to succeed. So we can go through this broil node because it does match, and we can keep going. Blue nodes are going to push things on. And so what this gadget has done is it's rewritten the lookup of unqualified stove into a qualified lookup of, unqualified lookup of broil into a qualified lookup of stove.broil, because that's what an import statement does, is it says go find it in this module. The other thing that an import statement does is it tells you to go look for that qualified reference in a different file. And so the other thing that the import gadget does is it takes you to the root node, because the root node is how you cross from one file to another. So now here we couldn't go right into the kitchen node because, again, the top of the stack has to match, and top of stack is not kitchen, so we can't go that way. We can only go left. And so we pop off the stove dot. This is the definition of the module that we just walked into. And then we can proceed up until we get to the broil definition, which pops the last element off the stack, and that leaves us with the binding path, which is valid. And we weren't able to go into saute or into bake, again, because that doesn't match top of stack. Okay, let's do this for the more complex example. We're going to skip the step where we look at the stack graphs for each file in isolation, and we're just going to show the combined graph as a whole. But again, just like before, there's a portion of the graph for each of the three files, and they're distinct from each other. The only place where they come together is that shared root node in the middle. And in this graph, it's still the case that there's a path from the broil reference to the broil definition. It's a much longer and more complex path because this is a more complex example, but the mechanics of what we did are going to be exactly the same. So we start at the reference, we push broil onto the stack. We actually push a couple of more things on because it's an instance member that we're looking for this time. So what we're actually trying to find is lowercase stove.broil. And now if you remember, the next thing that we have to do is figure out what stove refers to. And so because this is a stack, that sort of pause the later bits in order to do some earlier bits comes for free. That's just what stacks do. So we keep walking through the graph, and we're able to find, luckily, just one line above, that there's a definition of stove as a local variable. And we have attached to its definition nodes that describe what its value is. So if we move through those, we see that lowercase stove, the local variable, is the result of calling capital S stove. And again, we don't know what capital S stove is yet, but we have at least pushed onto the symbol stack that we need to go find that out so that we can continue our lookup. We keep going up further in the file. We have the same import statement gadget that we had before, which says that, you're looking for capital S stove, you probably need to go find that in the kitchen module. And because it's an import statement, go look for it in another file. So let's go to the root node. Now we can go up into kitchen.py, move through these nodes, which have the effect of replacing the lookup of kitchen.stove with a lookup of stove.stove. And again, it comes back down into the root node again because we have to go look for stove.stove in some other file. We can move down into stove.py, pop off the definition of the stove module. Now we're into the nodes that we created for the class definition itself. And so we pop off the name of the class, which is good. It matches what we're looking for. We've added this call node here because you are allowed to invoke classes in Python. And what you get as a result, this IM label is meant to stand for instance members. This is the scope that we created that holds all of the instance members of that class. And so if you invoke the class, you get an instance of the class. And inside of that, you can pop off your member access operator and go find the particular instance member that you're looking for. So it was still just a path. It went through a number of files. We pushed and popped a whole lot of stuff to make it work. But mechanically, it's the same thing that we did in the simpler example. OK, good. We're done, right? We did it. I'm going to hopefully say that no, we didn't. We're still doing too much work at query time. What I described works, and it is incremental in that the graphs that we create for each file depend only on the content of those files. And so we can reuse the graphs that we create if the file doesn't change. But at query time, we're doing a pretty expensive computation. We're loading all of those subgraphs, joining them together, and then doing this fairly expensive pathfinding operation in order to find the name binding lookups that we care about. And that works. It just has shifted too much of the work to query time. And so now we're going to violate that 100 millisecond budget that we talked about. So we want to shift more of the work to index time while still sort of having that same basic incremental shape that we talked about. And what we're going to use for that is this thing called partial paths. So now we're looking again at the stack graph that we created for one of these files in isolation. What we're going to do is we're going to do that pathfinding algorithm that before we did on the combined graph, but we're only going to do it just looking at the graph for this individual file. And it means we're not going to find a complete name binding result, but we're going to see how much of the result that we can calculate without having to move elsewhere. So in this case, we have this subpath that goes from the Broil reference to the root node, and we can describe that as what we call a partial path. It has a start node and an end node. In this case, the start node is that Broil reference, and the end node is the root node. And we also have what we call the precondition and postcondition. The precondition describes what has to be true of the symbol stack for us to be allowed to use this partial path, right? And we'll see an example of the precondition on the next slide. The postcondition tells us if we are allowed to use this partial path, what effect does it have on the symbol stack that we're building up? In this case, there is no precondition. You can start at that reference whenever you want. But if we were to use this partial path, right, it goes through a couple of push and pop nodes. The final result that it has on the symbol stack is that we will have pushed stove.broil onto it. And that's encoded in the postcondition. And what's really nice is that this is a sort of like rigorous or like data encoding of that English language fact that we talked about before. So the reference, that's the blue node, refers to stove.broil. The stove.broil part is encoded in the postcondition. In some other file, that's encoded in the fact that the end node is the root node, because that's how you move from one file to another. So this partial path is an encoding of that English language fact that we talked about before. We can do the same thing in stove.py. We have a path that goes from the root node to the definition. And so we have, the start node is root, the end node is that definition node. Now we have a precondition. We're not allowed to go through those red nodes because they pop things off the stack unless the stack contains the corresponding symbols. Otherwise, each of those pop nodes will be invalid and we can't use it. So there's a precondition that says the top of the stack needs to be stove.broil. Otherwise, we aren't legally allowed to go through those nodes and use this partial path. If we do use this partial path, we will have popped that content off, and so what's left in its place is nothing, empty symbol stack. And this corresponds with the fact that there is a definition called stove.broil at a particular location. And like before, we did this combination step on the English language facts. In the partial path world, that's an operation that we call concatenation. You can concatenate two partial paths, and it produces a new partial path. For that to be valid, the end node of the left-hand side must match the start node of the right-hand side, right? Because otherwise they wouldn't be able to join together. And the post-condition of the left and the precondition of the right have to be compatible with each other. And if they are, you can concatenate these two partial paths together. And this partial path, which starts a reference and ends at a definition, is a complete partial path. It's a silly name, but that's what we call it, which represents that overall name binding result. It starts at the reference, it ends at the definition, it tells you a valid mapping from one to the other. Okay, let's do it with a more complex example. Again, we're going to look for partial paths. In this case, we have one that starts at the root node and goes to the instance member node. It has these pop nodes as well, so we have a precondition. This corresponds with the fact that invoking stove.stove gives you an instance of the stove class. There's another path in this file, partial path in this file, that starts at the instance member node and goes to the broil definition. It has a precondition because there's pop nodes. This corresponds with the fact that the stove class has an instance member named broil. We're going to do the same thing for kitchen.py. This only has one path. It starts at the root node and ends at the root node, and it has both a precondition and a postcondition. And it encodes the fact that if you're looking for kitchen.anything, you might find it at stove.anything. And then in chef.py, this will be the doozy. There is a relatively long partial path from the broil reference to the root node. And we've pushed quite a lot of stuff onto the stack in order to get there. But if you just sort of read that off, it's actually going to line up very clearly with the English fact that we talked about before, that if you can find what kitchen.stove resolves to and you can call it, the result should have a member named broil, and that's what the reference refers to. And again, we can do this combination operator by concatenating partial paths. So we start off with the big one that starts at the reference, and we use our rewrite rule to change kitchen.stove into stove.stove, just like we did before. We load in the partial path that says that invoking the class gives you an instance of that class, and those are compatible, so we can merge them together. Then we load in the partial path that says that the class has an instance member at this particular location. Those are compatible, and we can merge them together, and we get the final complete path that tells us the result. Okay, are we done? We had this sort of list of 5 things that we were trying to accomplish. I would contend that we've solved these 2 pretty well. The bit where the result might depend on intermediate files, we need incremental processing. I think we have a good answer to that, right? The graphs that we create depend only on the content of individual files. We have this partial path mechanism that lets us pre-calculate a fair bit of work at index time and then just join them together. I think we have a pretty good answer to this. Different languages have different name binding rules. Some of those rules can be quite complex. Pretty good answer there as well, because we can create whatever graph structure we need to implement the semantics of the language that we're talking about. So that one I think we've done pretty well on. We'll sort of get into whether or not that's true in a second or two. We haven't really talked at all about the zero config part, because we haven't talked about how we create these stack graphs at all. I've just sort of waved my hands and said, oh, you can create a graph for this Python file. Well, how are we actually going to do that? For that, we're going to leverage TreeSitter, which if you're not familiar with TreeSitter, this is a project which lets you implement parsers for programming languages. It's a parser generator framework that GitHub originally created for use in the Atom text editor. We also use it for a number of other product features on GitHub, and it's developing a pretty thriving ecosystem. There's a lot of people starting to use TreeSitter outside of GitHub as well. You may have noticed, for instance, that NeoVim recently, in their 0.5 release, incorporated native support for TreeSitter syntax highlighting as well. So this is a language ecosystem that's starting to get more traction outside of GitHub. And what TreeSitter lets you do is you provide a grammar for your programming language, and it allows you to parse the raw source code into a syntax tree. And so this is the TreeSitter syntax tree for that file that we just saw. The other thing that TreeSitter gives you is this nice query syntax, which lets you look for patterns of nodes in that parsed tree content. And so this is a query that would let you look for any function definition anywhere in the file. And this at notation is what we call a capture, which lets you attach a label to some of the nodes that are coming out in each of the matches. And in particular, we have this name capture here, which is attaching to the identifier inside of the function definition that we just found. And so this query lets us extract out the name of every function that's defined anywhere in the file. This already exists. TreeSitter has the sort of grammar DSL for defining the grammars, the generation step that builds the parser from that, this query language that lets you look for patterns in the trees. That all exists. That's an existing part of the TreeSitter ecosystem. What we've added is this new graph construction DSL, which lets you attach to the TreeSitter queries these statements that let you produce arbitrary graphs that depend on the content of the parsed syntax tree that comes out of TreeSitter. And so this snippet here, creates a new node, attaches a couple of attributes to that node, and uses an edge to link that new node with a node that we created somewhere else in this graph.dsl file. And that corresponds with this, sort of like gadget of nodes that we might have created when I was showing you all of the stack graph instances earlier in the talk. So the idea is that for a particular language that you want to support, you write a graph.dsl file for that language that defines the rules for which particular gadgets of nodes and edges to create for all of the different kinds of language constructs that might come out of the parser. And what's important to call out there is that that means that we have a single implementation of the stack graph algorithms that I described. Treesitter itself is a single implementation of that parser generator step. And treesitter graph, this new graph.dsl that we're creating, is a single implementation of that graph.dsl. The only part that's different for each of the languages is that there are language-specific repositories that hold the grammar for Python and the syntax highlighting rules for Python and the fuzzy code navigation rules for Python. And now we hope eventually the stack graph rules for Python. And you'll see that some of these treesitter repos are in the treesitter org because those are ones that my team sort of developed ourselves in order to bootstrap this process. But you can also see that quite a lot of languages are starting to buy into this treesitter ecosystem and create their own repositories for their own languages. And so this is how we claim that we can support that long tail of languages that I talked about earlier, where we want to make sure that adding stack graph support for your language does not require a complex programming step. It does not require tapping into a long-running and possibly expensive build process. It's hopefully something that you can just create these declarative graph construction rules in order to generate the necessary stack graph content for your programming language. And so I contend that that means that we have found the right balance between index time and query time. So at index time, a new push comes in, we clone the files that have been changed, we parse them using the treesitter parser for that language. We construct the stack graph for that parsed content using the stack graph rules for that language. At that point, we are now done with all of the language-specific parts. We have a stack graph. We can run our partial path finding algorithm to get a list of the partial paths for that file, and we can stash them away in a database. Then at query time, we can see the reference that the user is clicking on and load in from that database the partial paths that we might need to satisfy that lookup and stitch them together using that combination, that concatenation operation that I showed you. And it is fast. We're finding that there's a prototype of this deployed internally that we have staff shipped for Python. We're hoping to get that released in the coming month or two as a GA release. We'll see. But it's fast. We're finding that index times, our median is 5 seconds, right? So you push the content before you have a chance to alt-tab over to your browser. We have indexed that and stored the partial paths in the database for later querying. And the stitching algorithm is fast enough that we're meeting those 100 millisecond budgets that we talked about earlier. Our median times are 50 milliseconds. Our P99s are right around 100. So it's working. I just want to leave you with a couple of even harder examples. This was a lot of dense content, and we actually have only scratched the surface of what stack graphs can do. So I want to show a couple of really, really hard examples here. So the one on the left is sort of like our canonical example of where sometimes lookup results depend on data flow. So if you look at what's happening, pass-through is a function that takes in a parameter and then immediately returns that as a new value. And so we want to be able to click on 1, the reference at the bottom, and have it go to 1, the definition inside of the class. But in order for that to work, we have to trace the fact that you passed in a particular parameter and got that back as a result. And so different invocations of pass-through will have different results depending on what parameters you pass in. And then the example on the right is an even more complex one, which is showing how in Java you have generic classes. And what we want in this example is that if you were to click on length at the end, you should be able to see that first off, we have some inheritance going on. So we need to go find the very first method, entry set, in our superclass. But we also need to see that it's not just the generic hash map that we've inherited from. We've inherited from a particular instantiation of hash map with string and string as the key and value types. And so when we go through this chain of methods, we need to propagate that information correctly so that when we get to the end, we know that it has to be string.length in particular that you're calling. And the stack framework works for both of these examples. It makes the formalism a little bit more complex. We actually have this thing called a scope stack next to the symbol stack as well, which I didn't talk about at all. But it also makes the gadgets that you create a little bit more complex. But it's still the same overall process, where it's a declarative language for constructing the graphs, and then this nicely incremental division of work between index time and query time. And with that, that's everything. So I have credits for some of the pictures that I included. And also, like if you're interested in learning more about this, definitely come check us out in our open source repositories. So thanks very much.